y'all. Darley Berry Jr. back for some more physics, doing another rendition of forces and scattering. So continuing this section, or a difficult section, I would say. So you could tell it is because we're spending, Friday will be our third day on this section, getting into it in a bit depth. So I'll go ahead and continue from where I left off. I just calculated the Rutherford scattering cross section, which is this equation here. So basically we can get the angle at which the particles scatter when deflected off of a force center. And we're going to continue from this part of the text here. In atomic physics, the concept of a total scattering cross section, sigma t, defined as this equation here, is of considerable importance. However, if we attempt to calculate the total cross section for Coulomb scattering by substitution of equation 3.102, the Rutherford scattering cross section, in this definition, we obtain an infinite result. The physical reason behind this behavior is not difficult to discern. From its definition, the total cross section, the number of particles scattered in all directions per unit time for unit incident intensity. Now, the Coulomb field is an example of a long-range force. Its effects extend to infinity. The very small deflections occur only for particles with very large impact parameters. Hence, all particles in the incident beam of infinite lateral extent will be scattered to some extent and must be included in the total scattering cross-section. Okay. So they're saying that if you include every possible scattering, then every single particle in existence technically is being scattered just by a very small amount. That's what I'm understanding. It is therefore clear that the infinite value for sigma t is not peculiar to the Coulomb field. It occurs in classical mechanics whenever the scattering field is different from zero in all distances, no matter how large. And it's saying sigma t is also infinite for Coulomb field in quantum mechanics, since it has been stated that equation 3.102 remains valid there. However, not all long-range forces rise to infinite total cross-sections in quantum mechanics. It turns out that all potentials, reading the footnote, that fall all faster at large distances than 1r squared produce a finite quantum mechanical total scattering cross-section. Interestingly enough, because we know quantum particles can tunnel, so quantum particles can pass through objects that classical particles technically couldn't. And they also won't be deflected by things that classical particles wouldn't. So I guess it's not ironic to think about it. Only if the force field cuts off, i.e. is zero beyond a certain distance, will the scattering cross-section be finite. Physically, such cutoff occurs for the Coulomb field of a nucleus as a result of the presence of the atomic electrons, which screen the nucleus and effectively cancel its charge outside the atom. It's interesting. So electrons effectively screen atomic nucleus. Canceling its charge outside the atom. In Rutherford scattering, the scattering angle theta is smooth monatomic. Is a smooth monatomic function of S, which is the impact parameter. Still not clear. I mean, let's have heard what all these terms mean, but I'm still not clear of the full implications. In equation 3.101, we see that as S decreases from infinity, theta increases monotonically from 0. Let's copy this down and we'll see. So S goes up, no, S goes down from infinity, theta goes up from 0. Reaching the value pi as S goes to 0. S is proportional to theta 0, and that's big theta. However, other types of behavior are possible in classical mechanics, requiring some modifications in the prescription of equation 3.93, which I'm sure I copied somewhere. Classical section. For example, with the repulsive potential and particle energy quantitatively of the nature shown in figure 3.21a, let me try to get this figure really fast. There we go. So, for example, with a repulsive potential, so this is the repulsive potential. In figure 3.21a, it is easy to see physically that the curve of big theta versus S may behave as indicated in 3.21b. Seems like we're looking at, this is that, and this is that. Thus, with very large values of the impact parameter as noted above, the particle always remains at large radial distances from the center of force. Suffers only minor diffraction. page 111. Makes sense forward from the force of minor deflection. At the other extreme, for s equals 0, the particle travels in a straight line into the center of force. And if the energy is greater than the maximum of the potential, it will continue on through the center without being scattered at all. Hence, for both limits in s, the scattering angle goes to 0. For very big or small s, no scatter. For some immediate values of s, the scatter angle must pass through the maximum big theta m. Maximum big theta is less than theta m, there will be two values of s that can give rise to the same scattering angle. Okay, so that means that if theta is less than theta m, so will contribute to the scattering cross section at that angle, and the equation 3.93 should accordingly be modified to the form copy this down. Let me see. So this is modified to be that equals sum I of si over sine big theta ds over d big theta I. And this is 3.103. And theta equals not theta m. The index I takes on the values 1 and 2. Okay? So this means that this equals S1 over sine theta ds over d theta 1 plus S2 over sine theta ds over d theta 2. And this is all 3.103. These are for these two values here, so I can put theta 1 and theta 2. So the figure 3.21. Of particular interest is the cross section at the maximum angle of scattering, theta m. The phenomena of the infant rise of the cross section followed by the abrupt disappearance is very similar to what occurs in the geometric optics of the scattering of sunlight by raindrops. On the basis of this similarity, the phenomena is called rainbow scattering. Okay, I guess the fact that you do see a rainbow at a certain spot. And this image says repulsive non-similar scattering potential and double value curve scattering angle big theta versus impact parameter S naught for sufficiently high energy. So far, the examples have been for purely repulsive scattering. If the scattering involves attractive forces, right? This is what we did today, attractive force scattering. So far, the examples have been for purely repulsive scattering. The scattering involves attractive forces, further complications may arise. The effect of attraction will be to pull the particle in towards the center instead of the repulsive deflection outward shown in figure 320. In consequence, the angle phi between the incoming direction and the periapsis direction may be greater than pi over 2. And the scattering angle as given by equation 3.94 is then negative. This in itself is no great difficulty, as clearly it is the magnitude of big theta that is involved in finding the cross-section. But under circumstances, big theta as calculated by equation 3.96 may be greater than 2 pi. That is, the particle undergoing scattering may circle the center of force for one or more revolutions before going off finally in the scattered direction. Okay? To see how this may occur physically, consider a scattering potential as shown as the S equals 0 curve in figure 3.22. Right? So let me go ahead and get this really fast. So we have this. Let me check something real fast. I have my research going on the side. Right, there we go. So let's take a look at this. X equals 0 curve. Probably should copy this because I'll probably draw on this for multiple problems or discussions. So right now we're looking at this curve here. S equals 0. To see how this may occur physically, consider a scattering potential as shown in the S equals 0 curve. In figure 3.22, it is typical of the intermolecular potentials assumed in many kinetic theory problems. An attractive potential at large distances falling off more rapidly than 1 over r squared. Kinetic theory has greater than 1 over r squared, but a rapidly rising repulsive potential at small distances. The other curves, look at this. So the x-axis is r. The y-axis is v. So versus impact parameter. Impact parameter S is a combined attractive and repulsive scattering potential, attractive and close when close over and far away, and the corresponding equivalent one-dimensional potential that has several values of the impact parameter S. So a low impact parameter at low radius, it seems to attract very well. It looks like there's a big well, and it could be bound. Hold up, sorry, I had it backwards. Attractive at large distances and repulsive close. The other curves in figure 3.22 show the effective one-dimensional potential VR. Equation 3.22 prime for values of the parameter impact parameter S equivalently various values of L. Let's take a look at that really fast. And thank you for joining. Let me know if you have any questions about anything. Oh, well, when I say 3.22 prime, I thought maybe it says equation 3.22 prime. Right. 3.22 prime again. Without scrolling too fast. Page missing? 3.23. Seems like a page is missing, but I don't see 3.22 prime. All right, well, Browns values of impact parameter S. This repulsive centrifugal barrier dominates at large R for all values of S greater than 0. The equivalent potential for small s will exhibit a hump. Now let us consider an incoming particle with impact parameter S1 and at the energy E1. So now we're looking here, and actually let me use the one that I copied. So now we're looking at impact parameter S1 and energy E1. This is our energy corresponding to the maximum hump. So this is the hump they're talking about. As noted in section 3.3, the difference between E1 and VR is proportional to the square the radial velocity at that distance. The difference between E1 and VR is proportional to the square of the radial velocity at that distance. Section 3.3. So let's go to section 3.3. That stuff really builds on itself in this text. So this does seem similar with the potential and the energy. So I think it's fair to say that E1 is V R prime proportional to the square of the radial velocity at that distance. VR squared. Define that. Okay, here we go. So they're saying, they're talking about that equation there. So V equals square root of 2 over M E minus VR. And that's equation 3.21. So V squared equals 2 over M E minus VR. So V squared is proportional to E minus V. Right. Well, understood that well enough. I was able to write what they intended proportionally. And this is VR. Incoming particle reaches R1, the location of the maximum in V. The radial velocity is 0. Indeed, recall from the discussion in section 3.6 that we have here the conditions for an unstable circular orbit at the distance R1. In the absence of any perturbation, the incoming particle with parameters E1 and S1, once having reached R, would circle around the center of force indefinitely at that distance without ever emerging. For the same impact parameter but at an energy E slightly higher than E1, no true circular orbit would be established. So is a circular orbit. However, when the particle is in the immediate vicinity of R1, the radial speed would be very small and the particle would spend a disproportionately large time in the neighborhood of the hub. Okay, so we're talking about an elliptical orbit where the object moves faster when it's far away. And that's reverse. It moves fast slower when it's far away. So the scene's reversed. planets' highly elliptical orbits move faster around the center of force so they could sweep out the same amount of area in the same amount of time. We were talking, I believe, one of the previous videos about the aerial velocity, whatever it's called, uh, 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 Kepler's second law, that the radius of the orbit sweeps out the same area in the same amount of time. The angular velocity v, meanwhile, will not be affected by the existence of a maximum, being given at r by 3.90. Theta dot equals L equals S1 over R1 squared 2 E over M. Let me check my class notes and see if we mentioned. Vaguely remember this S1 over R1 thing. Keep on going. Thus, in the time it takes the particle to go through the region of the hump, the angular velocity may have carried the particle through angles larger than 2 pi, or even multiples thereof, like a temporary orbit. In such instances, the classical scattering is said to exhibit orbiting or spiraling. As the impact parameter is increased, the weld and hump and the equivalent potential V tend to flatten out. So looking at this here, until at some parameter S2, there is only a point of inflection at V at an energy E2. Right, so we're talking about this inflection point here. For particle energies above E2, there will no longer be orbiting, but the combined effect of the attractive and repulsive components of the effective potential can lead, even in such cases, to zero deflection at some finite value of the impact parameter. At large energies and small impact parameters, effects are caused by the strongly repulsive potentials at small distances. And the scattering quantitatively resembles the behavior of Rutherford scattering. We have seen that the scattered particle may be deflected by more than pi when orbiting takes place. On the other hand, the observed scattering angles in the laboratory lies between 0 and pi. It is therefore helpful in such ambiguous cases to distinguish between a deflection angle psi, as calculated by the right-hand side of equations 3.96 and 3.97, on this right now. Be sure I wrote this down. the transformation of scattering today. Is therefore helpful in such ambiguous cases to distinguish between the deflection angle psi, is calculated by the right-hand sides of equation 3.96 and 3.97, and the observed scattering angle big theta. For given psi, the angle big theta is to be determined from the relation. Okay. Big theta equals plus or minus, set it at a capital psi minus 2m pi. M is greater than 0. The sign and the value of m are to be chosen such so that big theta lies between 0 and pi. Is between the sum in equation 3.103 sum in equation 3.1.3 then covers all values of psi leading to the same theta. Figure 3.23 figure 3.23. So let me get this image really fast. This image momentarily. I need to do some EM stuff. I think I'm going to do the EM homework this week. So I'll be back. Actually, I need to write a paper, so I may not be back later. But at least I shall be back tomorrow. Right? Right? Like I had a brief disconnect. I think we connected. Okay. So a brief disconnect there. All right, there we go. Needs to be working again. The orbiting that takes place for E equals E1 shows up as a singularity in the curve at S equals S1. Here. And notice that they mean a singularity as if You may be familiar with that demonstration where they have like a tarp pulled down and they roll bowling balls or tennis balls or whatever around it to simulate gravity. It's as if this energy here, this potential here, actually this psi is you know with an angle. Okay. Well, still figuring it out. But apparently they speak the language of a curvature of space. E is greater than E2 orbiting no longer takes place, but there's a rainbow effect at big theta equals negative big phi, although there is a non-vanishing cross-section at high scattering angles. Note that big theta vanishes at S equals S3. There's no scattering angle, which means from equation 3.93 that the cross-section becomes infinite in the far direction through the vanishing of sine theta. Okay, the sine of pi is 0, maybe. The cross-section can similarly become infinite in the backwards direction, providing S ds d theta remains finite at theta equals pi. These infinities in the forward or backward scattering angle are referred to as glory scattering, again in analogy to the corresponding phenomena in meteorological optics. And he gives the backwards glory is familiar to airplane travelers as the ring of light observed to encircle the shadow of the plane projected on clouds underneath. That's interesting. Saying there's clouds underneath the aircraft. You can see the shadow on the cloud, but then you can see light around the cloud, around the shadow of the plane on the cloud. A more general treatment would involve quantum corrections, but in some instances, quantum effects are small, as in the scattering of low-energy ions in crystal lattices, and the classical calculations are directly useful. Even when quantum mechanical corrections are important, it often suffices to use an approximation method, a semi-classical approximation for which a knowledge of the classical trajectory is required. So classical still forms the foundation of everything. Almost all potentials of practical interest, it is impossible to find an analytic form of the orbit in equation 3.96. Put up a 3.96. For variant forms is either approximated for particular readers of S or integrated numerically. So this is a very important formula, both of these. Transformation of scattering problem to laboratory coordinates. So this is what we did in school, in class today. So I may come back tomorrow, but that's what I'll do tomorrow. So I'll probably go get something to eat in a moment, then come back and write a paper I need to write, and maybe come back and still do some foundation, some EM stuff. But either way, I forgot I have to do the old problems. A lot to do. So either I'll come back and do some EM or come back and do some old foundation stuff. And tomorrow we'll do section 3.11, which is this section here. Section 3.11, transformation of the scattering problem to laboratory coordinates. We'll work on that tomorrow. So thanks to those who popped in. Drop a line next time. Like, subscribe if you haven't. That help me get to 1,000 subscribers. I'll see you all next time.